our seminar. Yes, and Jacob's a graduate student at Tufts University, and he's been working with Mark Hertzberg, and they've done some very interesting work on how existing LIGO data can provide constraints on quantum gravity, notably on, particularly on the state of the quantum state of the gravitational field. So welcome, and go ahead.
All right. Thank you very much for that nice introduction and inviting me to give the seminar today. So exactly as you said, I'll tell you about how we can use existing data to put a bound on the squeezing parameter of gravitational waves. So to begin, it'd be good to give a background of some ideas of how people usually think about quantum fluctuations and gravitation. And the usual way of thinking is that they must be very small. How can we possibly see quantum fluctuations at LIGO? And certainly looking at data, so there's some example of one event. They haven't seen any unknown correlations in these residuals. Sorry, my screen sharing seems to be doing something weird. Can everyone see still?
Yes.
All right, it's just me then. My screen has gone black.
Oh. Yeah, I don't see any of the Zoom controls or anything.
Maybe you can log back in to the Zoom session, maybe that, because we see your quantum fluctuations incredibly tiny screen.
Yeah, we see you on camera as well, and we see your screen.
Well, Aaron, could you stop the screen sharing for me? Is that possible? And I'll try starting again.
Yes.
I think it happened as soon as you said there was nothing quantum about gravitational waves.
Let's see.
Just joking. So.
All right, I see nothing. So, oh.
Yeah, now something new.
Now I see. Okay, maybe it was just a problem. Yeah, it was a problem with making my slides full screen for some reason. That made my screen go completely black.
Sometimes you can
that's all right.
share.
I'll just leave it like this.
Yeah, this is fine.
That's fine.
This is fine.
Sorry for the interruption. So, as I was saying, there's no unexplained correlations in these residuals. So it's usually the assumption that quantum fluctuations are unobservably small. And in the context of treating general relativity as an effective quantum field theory at large distances, we are thinking of the gravitational wave as being in a quantum state. It's usually thought of as a coherent quantum state, or in superposition of many gravitons in a coherent state. And then with that treatment, you typically find variants of quantum fluctuations are then something like 19 orders of magnitude smaller than the classical amplitude. So based on those assumptions, you shouldn't expect to see any quantum fluctuations at LIGO. And for more details on this kind of thinking, this follows work by Dyson and others, for example. Now, if this was the end of the story, then the talk would be over and we would all go home. But fortunately, it's not. So there's some important recent work from including some of the people here today that gives us a new interest in this topic. So in particular, in these recent papers, they were looking at the notion of test particles in the background of a quantized gravitational field, and found that there's a modification to the geodesic deviation. And you can think of the motion of the mirrors in an interferometer. So the motion is modified by this quantum noise of the quantized gravitational background. And these other terms are, H double dot is the standard tidal force due to the passing gravitational wave. And then you have this radiation reaction term. But if we go ahead and ignore that, so just to recap from these papers, if we ignore that radiation reaction, then you can compute simply the expectation value of the geodesic deviation, where the C naught is the unmodified length of the detector arm, for example. And then computing the variation from that, it just depends on this noise, which indicating is state dependent by this subscript psi. So they computed what the variation should be for various relevant states. And in particular for this coherent state, which is meant to be the most classical possible state, they found that it's Planck suppressed, proportional to the Planck length. So this ends up being very small, and there's basically no way to possibly observe this. But on the other hand, if for some various speculative reasons that we might discuss later, the wave can be set up in a squeezed quantum state, then fluctuations can be amplified by this squeezing parameter that I'll call zeta. So essentially pick up the factor of e to the zeta in this variance. And this kind of thinking and this result has been corroborated later by other authors as well. So essentially, based on these results, we want to see if we can compare to existing gravitational wave data and to put a bound on this squeezing parameter. And to do that, we have to make several assumptions, which I think are fairly reasonable. First of all, that the black hole or neutron star mergers that produce the gravitational wave C naught LIGO and set up a squeezed state. And we can talk a little bit more about why that would be reasonable later. And second assumption is that there's minimal decoherence of this state before the wave reaches the Earth and can be observed. So as long as these assumptions are reasonable, then we can go ahead and compute correlation functions for a class of squeezed gravitational wave states, and then compare the variance to that C naught LIGO to put a bound on this parameter. So that's the plan. And to get into the details of that, we first talk about a simple example that will set up the mathematics rather nicely. So we should all be familiar with the simple harmonic oscillator. So this is a familiar harmonic oscillator Hamiltonian, some natural frequency and some mass. And we can compute the ground state for this system. It just has a probability distribution that's Gaussian around some mean of 0. And this state minimizes fluctuations. So you can see that by the product sigma x sigma p is always minimized. It always has the smallest value h power 2 allowed by the uncertainty principle. Now we can generalize this a little bit to the coherent state, where we essentially just take this ground state and shift the position operator by some function x naught, which follows the classical equations of motion. So you have to get a shift in the phase as well. That's okay. And the probability, as I said, still just looks like this Gaussian, and now it's been shifted by this function x naught. And since this still minimizes the uncertainty principle, this is usually thought of as the most classical possible state. On average, the system just obeys the classical equation of motion, and the uncertainty principle is minimized for all time. So if we want something a little more interesting, we could have larger fluctuations. We can take this coherent state as the initial value of the wave function and insert some number beta in front of the quadratic term. This will control the amount of squeezing or stretching. And then we evolve this forward in time just by Schrodinger evolution. Now, okay, of course, the phase has to be modified a little bit. And now you end up with some time-dependent function in front of the quadratic term, which has this particular hyperbolic tangent relation to the initial squeezing. And why this is interesting is, well, now fluctuations can oscillate in time. And in particular, has a maximum that can be enhanced by either making this parameter beta very large or very small. So if you either stretch or squeeze the state a lot, then you can have large quantum fluctuations.
Sorry, can I just ask this? Function S of t is a property of the source? Sorry, what? No, maybe I missed. What is S of t?
Well, right, so all we've done is insert some number beta, can be any real number, and then to satisfy the Schrodinger equation, this S of t has to depend on beta in this way, but beta can still be any real number, and it still satisfies, it's still a solution of this Hamiltonian. So in this perspective, you have a class of allowed squeezed states. But any real beta is allowed.
Okay, I see.
And the time dependence of this squeezing is determined by the natural frequency of the harmonic oscillator. So the time dependence is governed by the system. So you have a class of squeezing functions depending on your choice of beta.
So this is another solution to the simple harmonic oscillator. That's
right.
Is this wave function in the box another solution to the Schrodinger equation for the simple harmonic oscillator?
Yes.
Okay.
Right. So to proceed, the kind of equations that I'll show for the gravitational case, we can compute the 2-point function of this state and see if beta equals 1, so there's no squeezing. So if S equals 1, then this is just a cosine. But if you allow for some S not equal to 1, then this can be enhanced. And I've written in this compact notation, but that kind of hides the fact that this is indeed invariant under interchange of T and T prime and complex conjugation, as it should be. So are there any other questions on that setup before we go to the gravitational case? Essentially, we can just put some indices on all of these terms and sum over them. I'll set that up a little more nicely now. So in the gravitational case, we start with the classical energy density of a gravitational wave propagating in the vacuum. And we can directly quantize this in the weak field limit by lifting h and its conjugate momentum pi to operators that obey the canonical commutation relation. And then going to Fourier space, our Hamiltonian operator is essentially just that harmonic oscillator Hamiltonian. We can essentially rename the things that appear in this equation. And now we just dress this up with some indices and sum over all of them. So, and we've already written this just in terms of the two polarization states. And the other thing we have to keep in mind is that in Fourier space, these operators can be complex. So in taking these sums, we have to keep in mind this condition that in configuration space, they're all real valued. So using that Hamiltonian, we can construct a coherent state and pass to a squeeze state. Now we just jump straight to that. And as I said, this looks very much like the harmonic oscillator state. We just dress everything up with some indices. And even added one more index just to make it more complicated, but just to break it up into the real and imaginary parts. And we see that this is just the same thing as the harmonic oscillator, but with a copy for the real and imaginary parts, the two polarizations, and all the wave vectors. So now at this stage, the parameter beta that appears inside these functions S can depend on polarization, the wave vector, even whether we're talking about the real or imaginary component. But if we want to compute variance in these states, then we're going to be integrating over all k. So we have to at least decide on the k dependence of the squeezing function.
So just to make sure I understand the notation, the k is obviously the wave vector number, the p is the polarization, and the a is whether it's real or imaginary?
That's right, yeah.
Okay, and so there's a beta parameter for all of those.
Yeah, thanks for the question. Definitely, if the equations get a little busy, please ask any clarifying questions or other questions. So we'll try to be as general as we can, but we at least need to decide on which modes, which k we're squeezing. And there are two simple choices we considered. So the as simple as possible one is to just say, we'll squeeze one mode. You can look at the LIGO data and say, well, this is the peak frequency observed. So we'll just say that single mode is the one we're squeezing. So that would correspond to a beta that looks like this, where K star is the squeezed mode. And now the remaining parameter that governs the strength of the squeezing is this zeta, which could still depend on the polarization. And just by convention, this appears as an exponential so that we can identify this zeta as the usual squeezing parameter. And maybe another choice, or maybe the next simplest choice would be to say we could squeeze some profile of modes around that peak. So the other choice we considered was to squeeze some Gaussian profile around that peak at K star with some width kappa. And at this point, I also wanted to mention that we haven't talked about this at all yet, but you would expect that the squeezing should only be appreciable around the center of the classical wave packet, but it should drop off going away from there. So you could insert some kind of modulating function into the 2-point function to take that into account. Where, for example, if you use an exponential, you can include the phase and the characteristic size of the classical wave packet to do that job. Or just to not add one more thing, well, just keep in mind for this talk that we're focusing on the center of the classical wave packet.
Sorry, can you say a bit more about this modulating function? Why do you have to assume it's there? What is
just based on the physical assumption that if there's some amount of squeezing taking place, it's on top of the classical gravitational wave, which is some wave packet that has some particular characteristic size. And so we wouldn't want to end up with correlations that are well outside of that, where it looks like there's some squeezing happening, far away from the center of the classical wave packet. That wouldn't be very physically realistic. So we could put this in by hand to make sure that quantum fluctuations only actually happen where there's a classical wave to begin with.
But I don't think that's necessarily true. You could even have a squeezed vacuum state, such as you'd have from inflation, which there's no accompanying classical coherent wave at all. So in that case, there would be some squeezing, but there would be no. There would be no coherent state on top of that.
That's true. If we're just interested in the fluctuations due to the classical wave that has some squeezed quantum state, so we can think about vacuum fluctuations as well, but they'll be separate. If we're just interested in fluctuations due to the wave, then they should be localized to a classical wave packet.
Right, possibly for black holes, this is a reasonable assumption because then you might expect that whatever is producing the classical coherent state is also producing the squeezing, and so maybe there's some. Maybe it has to be in roughly the same. It has to be centered around the same kind of classical wave packet, but I don't think it's generally. I don't think it's necessarily true that. I mean, there doesn't have to be a coherent wave at all.
Mm-hmm. Right.
In fact, that's if we could detect squeezing of a vacuum without a coherent wave, that would be even more promising because if such a thing were to exist, it'd be easier to find because we wouldn't have to actually wait for a signal. There would always be noise in the detector from the squeezed vacuum. And so we wouldn't just have to look at the noise during this fleeting signal that we might get from black holes. But anyway, go ahead.
Yeah, that's very interesting. Thanks for bringing that up. Yeah, maybe we can talk about that more later. But yeah, just to continue from these, we have these two choices. Maybe we put in some modulating function or what have you. We can compute the correlation functions for these two choices. And in either case, have some piece that corresponds to the unsqueezed coherent state. And then in both cases, another part that depends on how much the wave is squeezed. And so in our simplest choice, I think is actually too simple. So here we have some time dependence. So there's oscillating sine in both t and t prime. So we've somehow lost the time translation invariance. But in our Gaussian smoothed choice of squeezing, then everything seems to be fine. It's only a function of t minus t prime. So we choose to move forward with this choice of squeezing. And you can see where the dependence on the width kappa is. So if you are really interested in only squeezing one mode, you can make kappa very small. But it's interesting that if you a priori choose to squeeze only one mode in this way, then you get something that looks a little unphysical. So moving ahead with the second choice.
So 1 second, the thing on the left, the xi p is x prime t. This is the xi is the okay, so p means the polarization, right?
That's right.
So for a given polarization, this tells you the 2-point correlation between what's the index x mean there?
Right. Yeah, x and x prime are two different positions. So you can think of the locations of the mirrors.
Okay. So that's the separation of one mirror is at the origin, right? And the other mirror is at position x, and then is that right? And x prime, and then later on we're going to look at x prime and t prime.
Yeah, later on we're going to look at x equals to x prime to compute the variance based on this 2-point function. Okay, so if we want to do that, this involves integrating over all k. But if we're interested in the variance, which involves setting x equal to x prime, then even the coherent part, so it doesn't depend on the squeezing, diverges. So we have to introduce some response function or some frequency cutoff that takes into account the sensitivity of the detector. So, for example, we just put in an exponential, then we can perform this integral and get something finite. So that's some detail we have to take into account, but we can do that easily enough. And then, right, so for our particular choice of this class of squeezed states, we have this smooth Gaussian squeezing profile. We can look at the, this is from one particular event, seen at LIGO. We can compare the variance we would compute to the variance of this residual. And as I said at the beginning, there are no unexplained correlations in this residual. It just looks like a Gaussian with zero mean and very small variations around this size. So if we compute this variance from this class of squeeze states, and then choose the peak frequency based on the LIGO data, then this gives us a bound on the squeezing parameter zeta. And one thing to note is that this is a rather weak bound. So there's rather a lot of squeezing that's allowed just from this simple comparison. Right, so e to the zeta of 41, like 10 to the 16 or something. So there are allowed to be very squeezed states and still be within the observed residual.
So just to understand, to get this residual, you so there you took the observed and you subtracted out the classical wave, or what happened?
Essentially, but it's taking out the classical wave as predicted by numerical GR. So to have some predicted waveform from numerical GR, and so we didn't do that calculation. That's something that comes from LIGO. And they're also doing, these data they've done some smoothing already that we don't know all the details of. So one could try to go into all those things himself and maybe produce something with more detail, but that's essentially, that would just take what LIGO has done.
So wait a minute, you're saying that the data has already got some smoothing in it? So they have eliminated some noise that would be interesting to us?
Well, probably not. Like but I don't know exactly what is involved in the preparation of these data. They have some raw data and they do some smoothing, and that's something that I'm not familiar with. I don't know exactly what they're doing, but it's supposed to just be the raw data, and then the residual is supposed to be just the raw data minus the prediction from numerical general relativity.
Yeah.
So this is meant to include things like the seismic background and other sources like that, I believe. So you could try and get a more detailed bound by taking those into account before comparing to this residual.
Right. So what you did was you took this residual unexplained residual noise and then calculated its variance. Is that what you? And use that to bound the squeezing parameter.
That's right. Yeah, and just from this one event as well. So taking into account the other sources of noise that they believe to exist.
And why did you choose K star to be F star? I mean, and not say the peak frequency that LIGO is sensitive to?
Well, we chose F star to be a peak frequency from this event. So, if you look at all other events as well, then there would be in each of those data points would have some variance and some F star. So it's tailored to each event.
So that's again your idea that the form of the squeezing is related to the coherent state that's accompanying it, to the classical gravitational wave that's accompanying it. I mean, if there was no wave at all, for example, you would choose F star to be probably something like the maximum frequency that LIGO is sensitive to.
Yeah, so if you plug in the maximum frequency that LIGO is sensitive to, then if there would be a much larger amount of squeezing. So we think that this is realistic, that the squeezing depends on the classical wave packet. But a more conservative estimate would be to put in the highest frequency that LIGO is sensitive to.
No, that would go the other way, right? So if you made K star larger than what you've written, or F star larger than 200 hertz, then consistent with these observed sigma s, what is that? Zeta would be smaller, right? So it would be a tighter bound, actually. Probably not by much, but.
Mhm.
So I think F star could be, if LIGO is sensitive to about a kilohertz, so that's a factor of 5. So theta would be lower by a natural log of 5. Which is like 2. That's it.
Yeah. Yeah. So as I said before, what we have in mind is fluctuations localized to the classical wave packet. It's produced by some astrophysical source like a merger. So whatever squeezing comes with that, right? Okay, so just to summarize what I've mentioned so far, in the most classical possible state, just a regular coherent state, quantum fluctuations are predicted to be very small, so you wouldn't expect to be able to detect them. But in a squeezed quantum state, fluctuations can be enhanced by the squeezing parameter. And just a simple comparison to existing LIGO data allows us to bound that parameter and can maybe get a more detailed bound by considering all of the available data and perhaps taking into account other known sources on Earth that contribute to that residual. So that would provide a clear extension to this work, but maybe a more interesting related topic would be to think about the sources of these squeeze states to begin with. So for the gravitational waves seen at LIGO are understood to come from black hole or neutron star mergers. So we can think about whether these processes could produce gravitational waves in a squeeze state. Or, you know, in the early universe, the time-dependent background can squeeze vacuum fluctuations into a squeezed quantum state. So we could imagine that an analogous process happens in this case, but it would be interesting to try and do a calculation and see how that actually could happen. But on another note, I also expect that individual black holes can radiate gravitons via Hawking radiation, and that this would produce some thermal background noise. And in principle, that could provide the source for the geodesic deviation. However, there's no reason to expect that to be large enough to see the LIGO, as far as I know. Maybe other experts here have something to say on that.
Well, I think that if it's thermal, then it's not a squeeze state. So I think that produces a very small effect, as you said.
So, right, it would be interesting if there were other sources, either for a thermal background that could produce some appreciable effect, can be observable, or other sources of squeezed gravitational wave states. And if there are any other questions or comments, I'd be happy to hear this.
So
thank you, Jake. Yeah, Tammy, go ahead.
I forget. I think George explained to me a few times, and maybe Malik did too, but maybe Jacob can as well. What kind of sources produce squeeze states?
Well, so the example that I brought up is in inflation, where you have a time-dependent background that can squeeze vacuum fluctuations and produce very squeezed primordial gravitational waves.
So classical sources like maybe black hole collisions, would they produce squeeze states?
Well, that's the assumption. So it would be reasonable to assume that they would, but as far as I know, or I don't know of any calculation that has actually seen that. That would be interesting to do.
I thought it was some sort of general statement like if the interaction is linear, bilinear between the source and the current and the wave, then it'll be squeezed. But if it's quadratic, it'll be something else.
Yeah, that's exactly right. So we expect that when the even if you have a classical source, you can, if the interaction is strong, so that there's some nonlinear effect. So, for example, instead of your in your interaction Hamiltonian, instead of J phi, you had something like J phi squared. Then even if J is classical, you would generically produce a squeeze state rather than a coherent state.
But just a J phi would not produce squeeze state.
J phi would produce a coherent state.
Coherent state, I see, but not squeezed.
Yeah, but so whenever, but you have all these other higher couplings in gravity anyway, because it's a nonlinear theory. But so whenever you have strong gravitational fields, even with classical sources, you would expect there to be
some squeezing.
Some squeezing. Yeah. So I don't know whether that holds for you know, cosmic strings and other kinds of objects.
Yeah. Does it also depend on the source being relativistic? Because if it is, then these string cusps could maybe produce, because then they are very ultra relativistic. So, I mean, yeah, I don't know why relativistic would affect things, but
I'll have to ask Ken Olem about that.
So, sorry, what was that, Jacob?
I just said I'll have to ask Ken Olem about that.
Yeah, absolutely.
Yeah, I guess the question is, when can you, to what extent can you go beyond, you know, linearized gravity? And for black holes, we know that, especially at the final stage of the merger, there'll be nonlinear effects there. So whenever that's the case, you'd expect that would not be described quantum mechanically.
Well,
in fact, Frank has sort of posed generalization of squeezing called molding, which is not just phi squared, but phi cubed, phi fourth. Yeah, there'll be an infinite number of potentially more and more intractable kinds of states, but that could all have noise.
That are all just produced from higher and higher order corrections.
Yes, yeah.
I see.
But as you said, there's no actual calculation done. It's not such an easy calculation because it's nonlinear.
Right. Well, from what I understand, it's also potentially could be the case that if whatever the true nature of black holes is, so potentially very quantum objects, that could give rise to some process which can produce squeezed or high order molding potentially. If there's some other quantum effect that comes in at the same order as the next order correction just from classical GR.
Yeah, that's certainly also true. So the way we get coherent states is we have a classical source coupled weakly to a field. So we can become non-coherent by either making it strongly coupled or by making the source not classical. So, of course, if you think of the black hole as some kind of quantum object, inherently quantum object, then you could also get some unusual states. I don't know why those would be squeeze states, but whereas for the nonlinear effects, you're sort of guaranteed that they would be squeeze states.
Right. Yeah, that's very interesting.
So the effect of mergers from black holes will be very different from those from neutron stars.
In the case where if black holes are very intrinsically quantum objects, is that what you mean? Or just even if they're well described by classical geometry? Well, yeah, I think if they're intrinsically very quantum, then it would look very different depending on if they were black holes or neutron stars.
It seems to me that unlikely that neutron stars will give us also, the gravity is of course weaker than for black holes. So I think our best bet for squeezing really is black holes. Do you know what the LIGO sensitivity limits are? In other words, you mentioned that you could account for some of this residual noise by considering known sources of local noise like thermal fluctuations, photon shock noise, et cetera, right? There's all sorts of noise that they detect, which have nothing to do with quantum gravity. So if you eliminated all that, you'll get an even smaller fluctuation of the unexplained noise. Do you know? Yeah, so the strain would be even tinier for the unexplained part of the residual, I guess. Do you know how much smaller they can go?
I don't know what their best estimate is. So if they need to be sensitive to 10 to the minus 21. But whether they can go down to whether it's sensitive to 10 to the minus 20 or I don't know, or far below that, I don't know. At this point, of course, that would just improve this bound. But we don't know at this stage, at what order of magnitude we should have quantum fluctuations, because if they're in a squeeze state, we could potentially already see them, which is what gives us this fact.
Have you checked others LIGO signals, like those with larger black holes?
Sorry, what was the first part of your question?
So if you check with others, so here you only show one single signal, analysis of one signal, right?
Yeah, this is just from this one event, but there's nothing too unusual about this. This is a pretty vanilla observation. So we wouldn't expect the bound to be very different considering other events as well. But if you wanted to be completely thorough, you could consider all of the existing data. From our perspective, right, you would have a variance and a peak frequency associated with each event. So you would just have a different peak frequency for different mergers.
I see. Are there other questions from the audience?
I had a small question. Sorry if it is too basic, but I was confused as to why we did not model the binary black hole merger as a squeeze state and then compare it directly to the data. Why is it that you needed to compare it to the residual? why not do the change in the numerical GR in this side itself?
Sure. So the quantum fluctuations are on top of some classical background. So we are saying they won't actually modify the classical part that you would get from just numerical GR. So it's literally just on top of that. So if we were doing that whole calculation, it would just be identical to what they did plus the quantum fluctuations.
Okay.
So there's no reason to repeat that calculation exactly.
I see. Okay.
Do you know whether there's a correlated noise between the detectors, such as between Hanford and Livingston?
Not that I know of.
There's no, well,
I mean, I think
I thought there was.
they both look like basically Gaussian noise with order this size variance with zero mean. But between the two of them, I don't know of any known correlations.
Yeah, I heard that there was, but maybe I'm not, could be wrong, yeah.
Well, I wouldn't claim to be the most up to date on that either. So.
Are there other questions? If no, let's thank Jay again. Thank you.
Thanks for having me.
Thank you. Take care.
Thank you.
Thanks, nice talk.
You too. Thank you.